Good evening. My name is Majme Mirani, and I serve as the Dean of the College of Engineering at Embry-Riddle's Daytona Beach campus. It is my pleasure to welcome everyone to this webinar, including faculty, staff, and students in all three campuses, university leadership, President Butler, and our distinguished keynote speaker, Professor Daniel Hastings. The keynote address is the highlight of Engineers Week, which our college sponsors every year during the National Celebration of Innovators. This is the first year that the keynote address is delivered in a webinar format. The upside of that is that both our Prescott and worldwide campuses are participating. Engineers Week is always held in February to coincide with George Washington's actual birthday, February 22. It is observed by most engineering schools, education and cultural societies, and many corporations and government agencies. The purpose of Engineers Week is to bring public awareness to the profession of engineering and to what engineers do every day to make life better for all of us and to call attention to the contributions engineers make to society. It is also a time for engineers to promote STEM education among young generation through community outreach and to highlight the importance of it to our country's future prosperity and national security. As a bit of history trivia for the audience, I like to mention that our country's first president, George Washington, was a civil engineer. Well, actually, he was a surveyor. And thus, he is considered the nation's first engineer, hence the coinciding of E-Week with his birthday. As part of this welcome message, I'm supposed to tell you about what engineers do every day. However, I would prefer that you hear it from the man whose name is quintessentially associated with the marvel of engineering, an aeronautical engineer himself, Neil Armstrong. Let's watch a short video.
I am, and ever will be, a White Sox pocket protector nerdy engineer. Born under the second law of thermodynamics, seeped in the steam tables, in love with free body diagrams, transformed by Laplace and propelled by compressible flow. As an engineer, I take a substantial amount of pride in the accomplishments of my profession. Science is about what is, engineering is about what can be. Engineers' entire existence is dedicated to doing things better and more efficiently. It is a profession which leaves its imprint on our society in countless ways. A century ago, the world really needed improvements in quality of life, health, mobility, and living standards. At that time, life was a constant struggle. The 20th was a century often punctuated with the terror of war and darkened with societal struggles to overcome injustice. But the 20th was also the first century in which technology enabled the tenets and the images of those traumas to reach across the world and touch people in ways that were previously unimagined. Engineering helped create a world in which no injustice could be hidden. Many will look back to see how we have changed and what we have accomplished. The future's a bit foggy, but it's not unreasonable to suggest that the 21st century will enjoy a rate of progress not unlike the 20th. It's something to hope for.
Now for a few housekeeping details before we start the keynote address. In a moment, I will be inviting President Butler to introduce Dr. Hastings. Please feel free to submit questions through the chat channel during the talk. Given the time limitation, I apologize in advance if your questions does not get answered, but I still encourage everyone to submit questions. At this time, it is my great and distinct pleasure to invite Embry-Riddle President, Dr. Barry Butler, to introduce our speaker. Dr. Butler?
Thank you very much, Maj, and thank you for showing that video. That is just outstanding. It really states what we're all about. To those out there joining this webinar, all over 250, it looks like, of you, it's an honor at this time to introduce you to physicist and engineer Dr. Daniel Hastings, who heads up MIT's Department of Aeronautics and Astronautics. Acknowledging Dr. Hastings' achievement would take a lot of time, so I just want to highlight a few key points here so we can really appreciate having someone like him to help celebrate Engineers Week. Dr. Hastings is a researcher, he's an engineer, he's an educator, and his contributions to aerospace earned him membership in the prestigious National Academy of Engineering. He began his career with a degree from Oxford University, followed by a master's and doctorate in aeronautics and astronautics at MIT. And then he went on to serve later in his career as chief scientist for the United States Air Force and also chaired the Air Force Scientific Advisory Board. He was also a member of the National Science Board, all very, very significant positions in this country. Since becoming a professor at MIT in 1985, he shared his expertise on space environment interactions, rocket propulsion and space power and propulsion, space policy, and space system engineering. He's published extensively and wrote the book, Spacecraft Environment Interactions, a textbook I know a lot of you use, especially out at our Prescott campus. I was told it's part of one of the courses out there as a reference. Dr. Hastings has been an influential advocate for building the science and technology workforce that the world needs to reach our next great milestones in space. His perspective is international. He's a fellow of the International Astronautical Federation and the International Council in System Engineering. And he also served as director of the Singapore MIT Alliance for Research and Technology. Dr. Hastings is highly respected, not just for his research and leadership, but important is his advocacy for students. He works closely with his graduate students to advance the state of art in thinking about systems. So without further ado, we're very happy at this time to welcome Dr. Daniel Hastings. Dr. Hastings, thank you very much for joining us.
So thank you very much, Dr. Butler. It's an honor to be asked to give this presentation. I, like many of you, I'm sure, were moved by what Neil Armstrong actually had to say. Engineering has made a huge difference to the last century, and we hope will make an even bigger difference to this century. So with that, can you bring up my presentation, and I'll start talking about it. So I'm going to give you a perspective on the future of aerospace. So next, please. Well, what I'm going to do is talk first, give you what we did as a kind of a strategic plan process, because this is actually part of a strategic plan. Talk about the external enterprise research findings. I'm going to skip the education findings for the sake of time. Talk about some culture findings and then conclude. So next, please. So just to give you a little calibration, as a department, we're of course much smaller than Embry-Riddle. My department only has 38 faculty, 164 undergraduates, 259 graduate students, and a small number of postdocs. And I also gave you the demographics in terms of women and underrepresented minorities. That's actually important to what I'm going to come back to towards the end of this talk. So next, please. As I mentioned, this is actually the product of a strategic planning effort that we undertook in the department. And it's important to understand what the questions were. So the questions were, define what the critical challenges were for the aerospace enterprise for the next 20 years. And then
what is it that we, that is in this case the MIT Aeroastro department, could actually do that would have a tangible impact, because we can't do everything. And then where should we invest and what sets us apart? But really what I'm going to address is mainly the first one, what we saw as the critical challenges. So next, please. I want you to understand that of the 38 of us there were maybe 20 of the faculty who participated in this. And we did not just sit around talking to ourselves. We did a number of interviews internal to MIT. These are with different departments at MIT, department heads. We talked to colleagues in aerospace engineering in other parts of the country and in Europe primarily. We talked to lots of people in the government to get a sense of how the government was thinking, both people on the air side, the policy side, space side. And then we talked to lots of people in industry, all the big companies, Boeing, Airbus, Orbital, Lockheed Martin, BLUF, and so on, as well as talking to former colleagues. And it was out of all of this whole set of people that we formed these ideas. So next, please. Why did we do a strategic plan? It turns out that the department had actually done a strategic plan that was basically in the year 2012. And it was a good plan. But what was notable about it is that it had nothing about entrepreneurial aerospace. Actually, SpaceX wasn't mentioned in there. Blue Origin wasn't mentioned. Virgin wasn't mentioned. And so, it basically missed the rise of entrepreneurial aerospace. But of course, an awful lot of those things actually only happened in the last 5 years. So that's not too surprising. So those were the kind of the external drivers for a plan. And internally, there was a greatly increased emphasis on cultural issues, which I'm going to come back to. And MIT also decided to establish a new college of computing, which inside of MIT has been a huge influence upon where the institution is actually going. And I want to be clear, we already had a computer science department, but this was a recognition that computing was becoming a much bigger part of everything that was occurring at MIT. So those were all the big changes that forced us to say, let's do a strategic plan again. So next, please. So this is the bottom line up front. There's many interesting research areas of challenge in aerospace, and I'm going to go over them. But there's also serious and substantial challenges in diversity and inclusion in aerospace, and I'll show you the data on that too. So it's kind of a mixed message that you'll see as you actually go through this. So next, please. So we're going to talk about the external enterprise. So next, please. So my talk is going to be basically driven into really three different areas. I'm going to skip the technological trends and talk about what's happening in astronautics, what's happening in aeronautics, and then about some of the political and economic trends that we saw that were actually driving what was occurring. So next, please. I wanted to show you this. This set of ideas is actually from our friends at Boeing. And what it illustrates is the difference between what they sometimes call Breguet engineering, as in Breguet range equation, and what they now call heterogeneous engineering. So Breguet engineering is the idea that for aircraft, what you need to know is a Breguet range equation, which has things about the propulsion system, the structures, and so on and so on. And that was sufficient to figure out how to design an aircraft. And as I said, the ideas are actually from our friends at Boeing. What they're now saying is, no, the information system that the whole thing is connected to and talking to is also very important. And therefore, if you want to be the future of aerospace engineering is not just in the Breguet range equation, but in what they sometimes call beyond Breguet, the heterogeneous engineering. It brings in all the information technologies and computing to what's going on in aerospace engineering. So next, please. Okay, so let's talk about astronautics first. And the news is, of course, that there's new space-based businesses which are disrupting industries and creating novel products. So next, please. So this is a very interesting chart. It shows a set of services, if you want, or areas: space equipment, space services, space mining, space manufacturing, space tourism, telecommunications, geodata. And then looking at where things are. Are they marketed? Are they down or conceptual state? And you see a bunch of companies. These are all companies that are doing something in this space. The thing about this is, if you try to do this, here we're in 2021, if you tried to do this 8 or 9 years ago, this would have been essentially blank. Actually, 8 or 9 years ago, SpaceX barely existed, Blue didn't exist, Planet didn't exist, Astroscale didn't exist. The point to make here is that the space business, the astronautics business, is burgeoning with a whole bunch of new companies that are coming about, and they're not just doing the traditional things of telecommunications and observation from space. They're thinking about a whole range of different things: space tourism, manufacturing in space, space services. It's just expanding enormously. And of course, some of these are going to go out of business. There's no question in my mind about that, because that's the nature of what this is. But over time, you're going to see more and more things over on the right side get filled in as these companies develop the market in these areas. So next, please. Now, there are many things driving this, but here's one of them, which is the launch disruption. So, but mainly, of course, SpaceX has been disrupting the launch market. So you see here a comparison of the costs per kilogram of the Atlas and Delta, which of course are the traditional rockets produced by the traditional suppliers of Boeing and Lockheed Martin. And what SpaceX is able to offer, an 82% drop, 82% drop in launch cost per kilogram. That's just enormous. It means that for the first time now, the markets, people can consider getting up to space for costs which don't break the bank, which is what they were. It used to be said, if you launched on these Atlas and Delta, of course, it literally costs more than gold, to launch something into space. And you see here, of course, SpaceX is now dominating with terms of the launch activities, that they're actually doing. Now, but the issue is not just SpaceX. What you also see is the development of a bunch of smaller launch platforms that's worldwide. Rocket Labs, of course, is actually launching from New Zealand. Virgin Orbit is launching from a 747, which so far they've launched off the coast of the United States, but they can actually, in principle, fly to many parts of the world and launch from there. And many countries are developing the ability to launch small payloads into space, they're doing it at costs, as I said, which don't break the bank. So next, please. You just see here the growth of things being put up into space. The deployment rates increasing very substantially. And mainly, of course, what's being launched are small satellites, mainly the thing that's being launched. It's not to say the billion-dollar satellites are not still being launched, but the growth has been in the launch of small satellites, not all tiny satellites, but small ones. So next, please. Now, what's coming? You already see this happening. I'm showing you two different constellations. Actually, one of them is OneWeb, which went bankrupt and is now out of bankruptcy. SpaceX has put up Starlink. they're now starting to offer, I'm told you can now go to the web and try to get an internet connection through SpaceX for some price, but they're going to be offering worldwide broadband service to the world. Amazon is going to be putting up a constellation called Kuiper, which will do much of the same thing. And what you see is the growth of this new space enterprise, which is going to provide broadband to the world. It means that you can go anywhere in the world and get a broadband connection for rates, which of course not as good as you can get with fiber, but will be very substantial. I meant speeds as opposed to cost. So next, please. Now, that's not the only thing happening in the space business. So next, please. What you also see happening is the growth of the Space Force, and which President Trump put into action, and that of course was actually a response to something real, which is that more and more countries are recognizing both the strategic and tactical value of space, and deciding that the military has to have some role there. So the U.S. has recognized that. France has recognized that. They are now developing a space force. A number of other countries have actually done that. But in addition to that, you see this happening, which is the growth of the billionaires interested in space. So as you know, Jeff Bezos is investing in Blue Origin, Elon Musk for SpaceX, and Richard Branson for Virgin. And between these billionaires, and in addition to the small spacecraft launches, they are changing what's occurring in the space business. So next, please. Now, all is not perfect, because what's also happening is this, which is the growth of space debris. SpaceX says they're going to be, by the time they're finished, they'll put up 12,000 satellites. In all of human history so far, we've only launched about 6,000 satellites. And so the next couple of years, by the time they're done, they'll have double that number. It's already the case that there have been collisions in space between objects. And of course, a number of countries, China and India, and actually the United States, have shown that they can shoot down objects in space. This leads to space debris. Kessler at Johnson Space Center identified this phenomena called the Kessler syndrome, that you can get exponential growth of debris if things start colliding with each other. And the collisions cause exponential growth of debris. This is a serious problem that has to be solved in the next several years. If it's not solved, you're going to see a very different future than the one I just actually showed. So countries are thinking about that, and the United Nations is thinking about what to do there. So next, please. I mentioned the Space Force as something that is going to be a key part of what the United States actually does. Yeah, next, please. Now, of course, that's not the only thing going on in space. There's hypersonic concepts. So next, please. Both China and Russia have announced that they have developed hypersonic weapons. The US is developing a set of hypersonic weapons as well. SpaceX is actually developing not a hypersonic weapon, but a vehicle which they say will enable people to be delivered to the other side of the planet in half an hour. It will not be just a ballistic trajectory. It will actually fly out of the atmosphere and come back, and you'll be able to do that. So all of these things are, in a technological sense, now essentially upon us, and you're going to see continued advances in these areas. So next, please. I want to turn now to aeronautics to talk about commercial air transport, as well as what's happening with UAVs. So next, please. So this slide I'm going to show you here was actually created before COVID. And so this was the prediction of what was going to happen in terms of growth of traffic, before COVID. And so the expectation was significant growth through 2037, both in terms of traffic, in terms of aircraft, and so on. And most of the growth was expected to be in the Asian market, right? Well, COVID has hit. So next, please. Well, things, of course, have turned out differently. Worldwide passenger traffic in 2020 has dropped between 57 to 61%. And the projection is for a $395 billion loss gross passenger operating revenue in calendar year 2020. And that, if you just compare that to the other shocks like the financial crisis, SARS, and so on, you can see what's happened in 2020 is orders of magnitude larger than those other shocks. So next, please. Commercial jet orders have dropped off very substantially, both for Boeing and for Airbus. And you can see the changes here. Next, please. As well as the projected losses from various parts of the aviation enterprise. This is, of course, without any stimulus money. What United, American say they have to, people they have to let go, job losses of Boeing, Airbus, Raytheon, Rolls-Royce, GE, the jet engine manufacturers. So next, please. Now, that doesn't necessarily mean that all, from the viewpoint of the future of aeronautics is necessarily bad. It certainly means bad things in terms of job losses in the next few years. But there are opportunities that come for that. Because of the delays in aircraft and propulsion system coming online, there'll be opportunities for advanced technology insertion. I think everybody understands that the environmental pressure associated with aviation and the growth of the concern about sustainability is likely to cause there to be some changes in the aircraft that are brought on. Of course, the travel disruption is potentially stimulating the need for air taxis and urban mobility. The increased use of the internet is accelerating the demand for satellites. There's lots of potential opportunities for drone delivery. And this is actually an opportunity when air traffic is down to get improvements in air traffic management. So I'm not saying we believe that everything is bad, because we don't believe that. So next, please. The concerns about the environmental issues associated with aviation is going to come back at some point. I mean, McKinsey had a study recently where they said by 2023, 2024, it'll all be back. Then the concerns about environmental issues will come back. There are concerns about the pollution actually associated with aircraft, potential climate damages, aviation noise. We will all have to deal with those. I think COVID has just put those off for a little while. Yep, next, please. And you already see the aircraft companies responding to that. So Airbus has announced a set of what they call Airbus Zero aircraft concepts announced. They're talking about hydrogen-powered aircraft, more electric aircraft for short ranges. This is all associated with doing something about sustainability issues associated with aircraft. Next, please. And of course, lots of people are talking about electric aircraft, either all electric, all the way to partial turbo electric. Many different things you can do. Our thinking at MIT is electric may make some sense for short ranges, Boston to New York, for example. But for long ranges, Boston to Los Angeles, Boston to Tokyo, it's just hard to see how you can replace hydrocarbon fuels to actually do that. So we think it's going to be some kind of mix going into the future, but it is definitely going to change. So next, please. Let's talk a little bit about drones and air taxis, which are potential new markets. Next, please. There's already, of course, there are military applications for UAVs, but there's growing numbers of applications for civil applications in agriculture, in looking at pipelines, in communications and freight transport, last mile delivery, and of course in urban air mobility. So Airbus announced that the Olympics in Paris 2024, they're going to be running a set of autonomous air taxis to move people around Paris for that. So next, please. Just to show you what's already happening, these are 4 postdocs actually from MIT and from the Aeroastro department who came up with a UAV-based system. It's not just the UAV, it's the actual back-end data processing they do. The company's called Raptor Maps, and it does advanced crop analytics. They will fly over large farms and sense what's happening with the farmland, with the crops, do the processing, and provide the data back to the actual farmers. So this is a startup, and it's an example of one thing that, among others, that you can actually do with UAVs. So next, please. Of course, people are talking about last mile delivery a lot. So, Amazon now has received the approval to do that in a number of markets in the United States. And so you can expect to be getting your Amazon package, they say, 15 minutes from when you order it and pay for it. 15 minutes later, you might get a package that will come to your house delivered by a drone. Next, please. There are many, many players in this market developing a lot of different UAVs. One of the things both about these UAVs and about the small satellite business is that the price point has dropped to the point now where lots of people can come up with new innovative ideas and new designs of UAVs and of small satellites and do it at price points that don't break the bank. This is what's leading to enormous amounts of innovation and also the growth of entrepreneurs entering this business. So next, please. So I want to talk about that. So next, please. So here is a plot of a number of years of venture capital investment in the aerospace sector. This is not the billionaires. This is just VC firms entering the aerospace sector, both mainly the small satellite business and the UAV business. And what you see here is that in 2002, there was not much happening. By the time we 2018, a huge increase in the number of VC deals, as well as a huge increase in the number of investments, a factor of 11. So why is this? It's because these people see opportunity. And as I said, the price points for both small satellites and UAVs have dropped so that lots of people can try ideas. Some of them are going to fail, but some of them are not. So next, please. So here is, in this case, space technology investors, a number of different investment networks. And the point I want to show you here is both that there are a bunch of investors in this space and all the companies that they're investing in. And in addition to that, what you also see is the big companies, Boeing, Airbus, Honeywell, they all have Pratt & Whitney. They have their own venture capital arms. They are also investing in companies. And what they're doing, of course, is seeing how they develop and then snapping them up if they actually start developing, right? And what are they investing in? Autonomy, advanced manufacturing materials, connectivity, electrification, cybersecurity, and new space. Okay, next, please. Finally, let's turn to talk about demographic issues. So next, please. So this is where it's not such a good news story. So this is data from the aerospace department's Heads Association, it's called ADCA, Aerospace Department Heads Association. This shows there's something like 62 schools that are involved in this. This shows over a period of, look, over 20 years, right? More than 20 years, the percentage of undergraduates who are female and minority. And you know, what you see is you see two things. First of all, the percentages are low. And secondly, they're essentially almost flat over that period of time. I mean, you know, 15, 20%, not going much beyond that. So next, please. This is graduate enrollment, and you see the same thing. For women in aerospace engineering, it's flat. For minorities, it's flat. And actually for overseas students, it goes up and down a bit, but still, you know, pretty flat. So what that tells you is over that period of time, of course, there have been enormous efforts to attract both women and underrepresented minorities into the field. But of course, the demographics of the country have changed substantially over that period of time, but you couldn't tell it from looking at these plots. What it tells you is that aerospace engineering is not attracting women and minorities into the field. That's the conclusion here. Next, please. I just wanted to show you our class. So this is the Aeroastro department at MIT, a picture, that's a colored picture at the top, of our majors of 2019. 36% women, 24% unrepresented minority, and the picture of the people in the funny robes is the PhD students. 20% women, 8% minority. I mean, we're doing a bit better than national averages, but nowhere near what we want. And the contrast is with the class of 1925. For some reason, they all wore suits when they went to MIT then, but they're all men. So that at least has changed substantially, but still, we've got a long way to go. Next, please. Next, please. I wanted to just give you some of the research findings that came out of our doing all this data, collecting all this data from all of these people. And here's some quick ones here. As I said, post-Breguet, but post-Vannevar Bush world, in the sense of, you know, there's not a linear flow anymore between basic research to advanced development. But also post-Breguet, the issues that matter in aerospace engineering are not just the Breguet range equation, or for that matter, the rocket equation, but lots of issues associated with information technology. Increased entrepreneurship and private funding, the declining cost of access to space and new business models, change of air transportation, urban air mobility. I didn't mention all the new technologies entering, particularly additive manufacturing, autonomy, 3D printing, and so on. And the ability to do things at small scale, UAVs and CubeSats. These are changing the business. So next, please. I just thought I'd give you the top 10, the top set of things that emerge as challenges from talking to all these people. Issues in manufacturing and materials, model-based system engineering, additive manufacturing, issues of sustainable transportation, so particularly the effect of air transport on the environment, the issues of large numbers of UAVs being around and urban air mobility. The large numbers of UAVs are mainly an issue of noise as well as air traffic control, distributed small satellites, nuclear power and propulsion. I didn't really mention that, but that's actually a game changer for what you can do in space. Autonomy, autonomy, autonomy. We heard it so many different ways, but issue of trusted, verifiable, cyber secure autonomy, as well as hypersonics. So next, please. Finally, I'm going to end up with some leadership and culture finding. So at MIT in the Aero department, we're very proud of the fact that we have a bunch of very distinguished faculty, and you see some of them there, not including myself, but you see some of them there and what they've actually done. So, and that's a great service tradition for us. But next, please. But here's the interesting thing. We found by surveying our alumni that here's a plot which shows relative to the year of founding, and then how many years since they left the department, the number of companies being formed. And what you see is that our recent alumni, that is the 5-year one, 6 to 10-year one, are actually going out and founding companies. Lots of these small companies have been founded by our alumni. And when we talk to our younger faculty, most of our younger faculty said that, older faculty I might say, they weren't interested in following what we had done, going and serving in the government. What they were interested in doing is doing startups. So quite a number of our younger faculty now have their own startups. And that goes along with the fact that our students are also interested in doing startups. So what that tells us is that our education system has to be reoriented to acknowledge that fact. This is what our younger faculty and what our students actually want to do. So next, please. So we also addressed the question. I talked a bit about the diversity issues, and I've made the argument that aerospace is exciting. So why aren't there more women in aerospace engineering? I mean, women are 50% of the country. So why 20% in aerospace engineering? So what we did is we looked at our own population. Next, please. So this is survey data from our graduate students. We asked our graduates, our women graduate students and male graduate students, rate the extent to which the following factors have been obstacles to your academic progress: academic and social isolation, relationship with your advisor, whether it's been a major obstacle, a moderate obstacle, and so on. And what we found from the data, and you see the numbers of people who participated in it, is that our women graduate students said, by quite a larger percentage, said their relationship with their advisor was a major obstacle to what they were doing, and they felt more academically and socially isolated. This is our students in the department, right? So we conclude that this is part of the problem. We don't have an attractive environment for the outstanding women who are out there, to want to come into aerospace engineering. So next, please. So our conclusion is we must be committed to a culture of diversity and inclusion for our women, for our underrepresented minorities, for undergraduates, for our graduates, for our faculty. And the issue with that I just showed you is not just a retention issue. It's not just a recruitment issue. It's a retention issue. It's a culture issue that we have to deal with. So next, please. So let me conclude by what I said earlier. Next, please. My conclusion is there are lots of interesting research areas of challenge in aerospace, and I gave you a set of those areas. In both aeronautics and in astronautics, fascinating things are happening, mainly because of the dropping of the price points with launch, with UAVs, with small satellites, with the billionaires entering, entrepreneurship, small companies. It's the most exciting time in aerospace that I've seen in a very long time. But we also have serious and substantial challenges in diversity and inclusion in aerospace that we as a community must address if we want to see changes in the field. So with that, let me at this point end and see what questions people actually have.
Thank you, Dr. Hastings. After a thunderous round of virtual applause, as I am sure audience have had, we'll now open the floor to the question and answer, which I will moderate. We'll start with some of the questions that were submitted during registration and some during the chat. And I noted that I reviewed this questions, and I noted that you referenced to essentially all of them in your talk, but we go back and revisit some of them. First question that was asked is related to, the question says, is to sustainability, which you referenced. How do your ideas fit into conservation of scarce resources?
Yeah. So let me make an observation. One of the things we did is we went and talked to the CTOs of the major aerospace companies, both here, and we also went to Europe. We went and talked to AIRBUS. And you know, when I talked to the CTO of Boeing and the CTO of Lockheed Martin, I got a range of answers about what they thought were the big issues. When I went and talked to the CTO of AIRBUS, I said to her, tell me your top 3 issues. And she said, zero carbon, zero carbon, zero carbon. It's just a much bigger issue in Europe, you know. They were faced with the fact that at that point, this was pre-COVID, there was the growth of what they call flight shaming in Europe, and they had to address this issue. Now, I also heard it from the CTO of Boeing and Lockheed Martin, but it wasn't the top 3. It was like number 5 or 6. It just shows you there's a difference between Europe and the United States. I think the reality is in both places, and I believe also in Asia, there's a growing realization that the astronautics business is both a contributor to issues that affect sustainability, but both in a negative way, but also can also be a contributor in a positive way, right? So clearly, in a positive way, aerospace is in the business of delivering on monitoring. I mean, the reason we know a lot about what's going on is because there are satellites up there which are taking, you know, both pictures and doing measurements of carbon dioxide and water and in the atmosphere and so on and so on. In both cases, you know, this is both aircraft and spacecraft. This is really important because otherwise we don't know what to do, right? So that's really important. But also, of course, on the air side, you know, jet engines contribute to a certain amount of emissions, you know, into the atmosphere. That, you know, that percentage, if you look at the percentage, it's order 5% right now. And if you look at the projections pre-COVID, it was projected to go to order 10%. So, I mean, not as large as what automobiles and trucks do, but nevertheless, not trivial. Now, all of the major aerospace companies have committed. They actually did this at the Paris Air Show in 2019. They are committed to reducing that percentage. So, because, you know, this is not a good thing, because we care about the environment. And actually, in our own rethinking of our mission statement, we deliberately put into our mission statement that we were interested in what aerospace would do for a sustainable environment, which is, you know, different. If you looked at the mission statement that we had, say, 20 years ago, it was what we characterize as higher, faster, further. We're only interested in going faster or higher or quicker. You know, who cares about the environment? But now we say we do care about it, and it's important. And actually, we also think that's part of the reason why we're not as attractive to a broad range of people. If all you care about is higher, faster, further, you'll get a certain segment of the population. But if you show you're interested broadly in affecting society, which we are, then you'll get a broader segment of society. So we're interested in doing that. We think it's important. We understand that aerospace contributes negatively, but can also contribute positively. And we are committed to that. And actually, as I said, if you look at what the aerospace companies have said, they actually also committed to that.
Thank you. Next question is about manufacturing in space. It reads, I'm curious on your thoughts about the future of orbital manufacturing and refining as well as resource extraction.
So yeah, that's a very interesting subject. I'm actually part of a group right now, which is a NASA, Air Force, Blue Origin, SpaceX, a bunch of companies are involved group that we're talking about in-space manufacturing issues. So first of all, in a technological sense, we have shown that we can do it, right? Actually, space station was actually manufactured in space, right? The parts were launched on shuttle, put up, and literally put together by the astronauts, right? There's actually a 3D printer up on the space station right now, which can 3D print a small amount of material, small amount of things. So in a technological sense, we've shown we can do at least a relative, because I was going to say a small scale station is not that small actually, but it can be done. The critical question will be, for it to be broadly adopted, will the people who are in the business of making money in space be able to get into that business? That is, can you do a profit and loss enterprise with manufacturing in space, as opposed to doing by the government, which is what the space station is, right? I would say right now the jury is out on that. What is the case so far with station is that almost everything that they actually thought they could do on station manufacturing space, having done it there, people have subsequently figured out how to manufacture it on the ground. So it hasn't yet proven itself in that sense. Now, if you say, however, that we want to do mainly large things, as in kilometer size arrays, for example, say for radio astronomy, there's no way we can launch that from the ground. You couldn't. There's no launcher that will take it, right? Yeah, I mean, you'd have to manufacture that in space, right? So I mean, I'm at the moment agnostic on whether or not a profit and loss enterprise can be done. Now, in terms of resource extraction, again, of course, we haven't really done resource extraction from the moon, although people say that it can be done. There's no conceptual reason that it couldn't be done. There's something that just landed on Mars, that Perseverance landed on Mars, actually has an experiment on it called MOXIE, which is going to do resource extraction from Mars. They're going to extract oxygen from the atmosphere by breaking up carbon dioxide. So I think not only conceptually it can be done, but also that technology will prove it. The issue again will come down to, can it move beyond just an experiment to something that somebody who's in the profit and loss business, will actually be able to make a profit from it? I think the jury is still out on that. In terms of resource extraction from the moon, which of course is the easiest for us to get to, the NASA says it has plans to process lunar regolith, to extract water from the southern pole of the moon and use it, by melting the ice that's there. Okay, fine. I think technologically it can be done. The question is cost and whether or not it makes sense to anybody who's going to try to make a profit off of it. So I think the jury is still out. The technology is not out. It's the question of whether or not you can actually costs down to the point where somebody will make money off of it. Then you'll see things actually happening. Right?
Thank you. This question is from Magnus Bergman. He asked, what do you think of the future of lighter than air and hybrid aircraft, given their general lower, fewer per payload ton requirements?
Yeah, so interesting. People are looking again at lighter than air, vehicles. Actually, Lockheed Martin has been doing something around lighter than air vehicles. Why not? I think as people think about the issues of sustainability, a range of, in the system sense, a range of solutions will be considered. The reason I mentioned Lockheed Martin, I went out there to Lockheed Martin last year, and they showed me actually an airship that they were actually developing, which could carry a substantial amount of freight. I mean, if you didn't care about how long it took to deliver the freight from one place to the other, this could do a pretty good job. And so why the answer is yeah. I mean, it's conceivable. I think as we think about a range of different options for delivery of in this case goods, sure.
Thank you. The next question is from your counterpart here, Dr. Tassos Larensis, our chair of Aerospace Engineering Department. He asks, what should we change in aerospace education to address the future research directions that you showed us today?
That's a very good question. So a number of things. So I made the point that a modern aerospace vehicle is not just about the Breguet range equation or the rocket equation. Right? So a traditional model which just looks at aerospace's structures and propulsion and fuel and that kind of stuff, and aerodynamics, and does not capture what's going on in modern aerospace. Right? As a matter of fact, if you look at where the frontiers are, an awful lot of the frontiers with, say, UAVs are not so much in the actual design per se of a UAV, but in how the UAV talks to the other UAVs around it, how it interacts in the system that controls the whole. So I think, taking into account all the, let's call it, information technologies associated with aerospace vehicles, is critical. And let me be even stronger than that. If you look at CubeSats, for example, I think CubeSats are rapidly approaching the point where they will become just commodities. The fact that you can just buy a CubeSat, you can find a launch vehicle, put it up, and it's a commodity, tells you something. And as anybody who studies business will tell you, being in the commodity business is not a good business to be in, because you're just driven by to lowest cost. So I think that's one thing. Secondly, I think that's why I mentioned our mission statement. I think aerospace departments have to have a broader view of the impact of aerospace. That's why we changed our mission statement to emphasize caring about the environment, right? Which I said, you could just go look at our mission statement 20 years ago, it just wasn't there, right? It's a statement that we have to be responsible stewards of where we are. So I think part of the change of aerospace education has to bring those kind of emphases, into what we actually do, right? Now, this also tells you something else, by the way, that the connections to other fields of engineering are going up. Connections to material science, mechanical engineering, to electrical engineering, computer science are also critically important, because it's collectively how we will solve some of these problems.
Thank you. This question comes from an MIT graduate,
Okay.
our distinguished chair of electrical and computer engineering, computer science department, Dr. Tim Wilson. He asks, so how do we, a bunch of academic engineers, learn how to do cultural change? It's not something we have been trained in. Where do the resources to support learning how to make such changes come from?
Is an excellent question. I think the first thing you got to do, we're engineers. We're driven by, first of all, I believe, data. First thing you got to do is get data, right? That's why I showed you that data, right? So, I mean, I showed you the ADCA data, but that's why we went and gathered data. We asked the question, why aren't we attracting more women? This is so exciting. Why aren't we doing that? So we talked to our students. We actually have survey data from our faculty as well. We looked at retention data for across a number of years for both women and underrepresented minorities. Lots of data. And what the data very clearly told us is we have a problem. So that's the first thing you do. You're not going to make cultural change without acknowledging on the basis of data that you have a problem. So first thing we do is we admit we got a problem. Okay, now what do we do? Once you admit you got a problem, then you say, well, what can we do to substantially address that problem? I mean, not just by ourselves. I mean, in this case, we asked for resources from the School of Engineering and from the institution, to help us address that problem. We set up what's called a diversity, equity, and inclusion committee, which is composed of faculty, staff, and students, both undergraduates and graduates in the department. We got the resources from the institute, actually, to hire a DEI officer, a staff person who's an officer for that committee to help us. And she's an expert in the sort of things we got to do. And, we've raised resources in terms of fellowships, and we're going at the problem every way we can. We've had talks, we've had discussions, we've raised awareness. We're going at the problem every way we can. Culture change is possible, but it takes time. I should have said that I didn't show you that, but one of the first things we did in our strategic planning process is we wrote down an agreed upon set of values, because we said, here are the values that we live by. And if we're not living up to these values, then what are we doing? And those values include that we want to be an inclusive, supportive community. Now, we're not living up to those values. The data shows that. But by saying it explicitly and getting consensus in the department, it's a way of starting to address the problem. I'm not saying we solved the problem. I believe we started to address the problem.
Thank you. Along the same line, this is more for FYI, a comment from our Dean of Engineering at Prescott. He says, our aerospace engineering programs at Daytona and Prescott have 23.9 and 21.1% women in our undergraduate programs. Within our Astro option in AE, the percentage is significantly higher.
Good.
Any idea on how to attract young women into the aero side of AE?
Well, that's a very good question. So like I said, first of all, we believe both sides, aero and space, are exciting. So first of all, get across the excitement of the field, right? But secondly, this is part of the reason why we shifted the emphasis in our mission statement and also in the kind of research that we're actually doing. Our observation is certainly this is true at MIT. I don't want to get into just saying things that some people might perceive as stereotypes. But our observation at MIT is that, you know, at the undergraduate level, the percentage of women is almost 50%. It's I think 47% now. Okay. Most of them go into engineering, so that's good. But where do they go? They go into chemical engineering and biological engineering. They don't come to aerospace engineering. They actually don't come to electrical engineering, computer science, which also has an issue, and they don't come to mechanical. So why is that? There are many reasons for it, I'm sure. But we know one of the reasons from our surveys is you know, those other fields are perceived as being, let's call it, better contributors to the overall welfare of society than, you know, we are. We know that from our surveys. We have people tell us, that's why I kept on mentioning higher, faster, further. All you're interested in is going higher and faster and further, right? And you build fighter jets, right, which bomb people, right? Well, we do. But we also care about a whole range of other things, right? And we want to get across the whole range of things that we care about. We care about the impact of the environment. We care about justice from that. We want to get across the whole range of things. And we believe that will help us to attract, you know, more women. We believe.
Thank you. One more question from a professor. He says, very informative talk, thanks. What do you think is a healthy ratio between PhD to undergraduate students in an AE department?
A healthy ratio. Oh, that's a good question. I'll have to think about that. Well, first of all, let me make a philosophical point, which is I don't believe any department, by the way, should be producing more PhDs than the field actually can absorb, because otherwise all you'll get is unemployed PhDs, right? Okay. Now, it is the case in aerospace engineering. I know if I talked 10 years ago to our PhDs, I said, how many of you want to be academics? Every hand goes up. Okay. But do most of them end up as academics? Actually, the answer is no. Now, what we are observing is many more of them, that's where I showed you the data, are ending up as entrepreneurs, which is great. I think that's just great. So I think, you know, the field, so I don't know, I'm not sure I can come up with an answer, but I think the field has to come to equilibrium with, you know, what's the demand out there to employ people with PhDs. And, you know, right now, actually, in the entrepreneurial sector, there's a lot of demand because, you know, there's a lot of interest in what you can actually do. So I'm not giving a direct answer because I'll have to try to think about that.
Thank you very much. I give you a couple more. Do you think the next generation of engineers will make history as well as the last generation did?
Yes, yes. I mean, Neil Armstrong was cited earlier, of course, made history. The reality is the National Academy of Engineering at the turn of the century had a list of the top 20 inventions, you know, which have changed society. And they included things like development of clean water, electrification, and so on. I mean, just think how much that changed society. I think in this century, you know, the same thing is likely to happen. I mean, the advances in engineering, both biological engineering, information-oriented engineering, are just continuing. And it is continuing to change our society. So the answer is yes, right? Now, having said that, there was a survey done by, again, by the NAE, again, actually just around the turn of the century, about essentially public understanding of engineering. And what it showed was that most people in the public did not know what engineers do. And there is no better signal of that when people say that to get into space is rocket science. No, it's not. It's rocket engineering. It's not scientists who do that, it's engineers. And most people don't understand the difference between science and engineering. Actually, Armstrong said it very well in that vignette. So I just hope that the public will come to appreciate what we as engineers bring to bear on society.
Thank you. I appreciate that. Is there anything that won't recover in the aviation industry due to COVID-19? This should be a question from our colleagues in the College of Aviation.
So, there's two diametrically opposed positions on that. I mentioned there's actually a McKinsey study out, which they say that basically you'll see a recovery by 2023, 2024, and it'll be back to how it was, right? People want to travel and so on and so on. Okay. That's one perspective. Of course, the other perspective is just what we're doing now. What has this horrible COVID pandemic shown us? It has shown us that we can do a great deal over the internet. We have high enough bandwidth connections worldwide, not to every place in the world, but worldwide, that you can do lots of things. So I'm giving this seminar, obviously by means of an high-speed bandwidth connection, but I actually participated a couple of months ago I was moderating a session in a conference where the conference was nominally in Singapore. I was the moderator sitting in the Boston area. There was a speaker who was in Maine. There was another speaker who was in Washington. There were people in Singapore, and actually all the IT people were in Sydney, Australia. And you know what? You couldn't tell the difference. You couldn't tell. It was completely seamless, went smoothly, other than the fact it was different. You could tell looking outside, it was dark here and it was light there in Singapore, right? But you couldn't tell. So what does that mean? I certainly believe that is going to affect certainly our business travel. Business travel is quite expensive, and why you need to go to the other side of the world all the time to do something when you could do this, I'm not convinced. As was mentioned earlier, I ran this program in Singapore for 5 years. So the good news is this: I could get on a plane in Boston, change in Tokyo. It was 13 hours, Boston to Tokyo, one flight. On the ground, 2 hours, 8 hours into Singapore. All right. So, the sum of that thing is, literally 23 hours of travel to get there. All right. Needless to say, I was exhausted every time I did it. Hey, you know what? As long as I'm willing to stay up late, I can talk to my colleagues in Singapore now like this, and I'm not tired.
I completely agree. I think that's why I still hold in my portfolio of stocks Zoom.
Yes.
Even though vaccine is around.
Yes. So you've got to say this is going to have an effect on business travel.
There are a lot of good questions, but time has defeated us. But I'd like to conclude with a last question, this being Engineers Week. Someone has asked, how can I become a great engineer?
Wow, that's a really good question. I don't know who the individual is. So if they're an undergraduate, I would say really get the fundamentals under your belt, right? First, all great engineers, first of all, know something in engineering, really well, right? Know something. And actually, if you look at one of the things that I participated in several years ago was a study which looked at the development of people who are called system engineers in the companies. And they all started out as disciplinary engineers and then became system engineers, right? So, if that's a direction somebody wants to go in, I would say do know something really well, and then move on to this more broad kind of system engineering. Now, having said that, I think right now, as I've said several times, there's just an awful lot of opportunities in the entrepreneurial space. So if you want to become a great engineer, do something in entrepreneurial space. Look, 60% of startups fail. So 60% probably will fail, but some fractions succeed. It's worth a try. I think it's worth a try. There's a chance to do really great things.
Thank you very much, Dr. Hastings, again, for the wonderful presentation. I think our students, alumni, and guests are coming away with a whole new and more insightful perspective on the aerospace and aviation industries. We are truly honored you were able to join us for Engineers Week tonight.
Thank you.
In closing, I also would like to thank our attendees for tuning in. And for the engineers in the audience, I wish you a happy Engineers Week. I hope you are able to share your passion to inspire a new generation of innovators to join our profession. For more events of this week, please visit our website. Thank you and good night.